Hi everyone, my name is Megan Flynn and I will be going through the second part of Chapter 2 in the Concepts of Biology Openstax textbook. So you can find that link for the Openstax textbook at openstax.org. And since this is the second video of 3 for Chapter 2, do make sure that you are clicking that subscribe button so that you don't miss the order of each of the videos. So I have already gone over the first part of Chapter 2 from our Openstax Concepts of Biology textbook. So again, if you didn't get a chance to look at that video, it is available on my channel for 2.1, the building blocks of molecules. So in this video, we will be covering the second part of Chapter 2, which goes into water. So why water is so important for life. So as far as the learning objectives for this section, by the end of this video, you should be able to describe the properties of water that are critical to maintaining life. Okay, so we'll go through reviewing a little bit about the water molecule from my last video, and then learning why it is so essential for living things. So what is it about that water molecule that's so important for maintaining life? So first off, in the last video, we learned a little bit about water's polarity. So if you recall from before, we learned about covalent bonds. Okay, so covalent bonds occur between, it's the sharing of electrons within a water molecule in this case. So the oxygen and the hydrogen, they are sharing their electrons to fill their outermost valence shell. And in doing so, they have a very strong bond that holds them together. Okay. We also talked about in the last video how the sharing of electrons is a little unequal because of oxygen's electronegative capacity. And so the oxygen atom in this water molecule will hold on to that electron more often than it gets swung around to the hydrogen side. So as that electron is circulating the oxygen atom, it only occasionally makes its way over to the hydrogen side. So that means that the oxygen atom has the electron that they're sharing more often. And so on this end of the water molecule, the oxygen side, we get a slightly negative charge or a partial negative charge. Okay. Since the hydrogen atom does not get that electron very often, it's usually hanging around the oxygen, we end up with a slightly positive end, partial positive charge. Okay, and because of that, even though we have a covalent bond, that unequal sharing makes it a polar covalent bond. And since it's polar, we have that ability to form hydrogen bonds between water molecules. Okay, so remember that hydrogen has the partially positive end, and then a nearby oxygen or nearby water molecule, the oxygen end, would have a partially negative. And so these two would be attracted to each other. And so that attraction leads to a temporary weak bond called a hydrogen bond. And so the hydrogen bond forms between two water molecules, whereas the polar covalent bond occurs within the water molecules. And because of these properties, water's polarity, we can see that any polar substance that interacts readily with or dissolves in water is known as hydrophilic. Okay, so because of that partially positive, partially negative end of water, it's going to be pretty attracted to other polar substances that have the same kind of ability. And so those polar substances are hydrophilic. So hydro means water, philic means liking. So these are substances that are attracted to the water molecules. Okay, So there's a lot of examples of hydrophilic molecules that can dissolve. Basically, they dissolve in the water, or they readily interact with water molecules. So anytime, let's say that you are making a drink mix, okay? So you have water and you got some, I don't know, Kool-Aid or something like that, and you poured it in there. And at first the Kool-Aid's kind of this, granular substance, right? But the moment you place it in the water and you stir it up, it dissolves completely into the water because it's a polar substance. So it is hydrophilic. Now, compounds that are nonpolar compounds, meaning they share their electrons equally, they don't have a partially positive, partially negative end like a polar molecule. And because of that, they're not going to want to interact with a polar molecule. They're not attracted to them. And so we call those substances hydrophobic. Hydro means water, phobic means fearing. So they're not going to want to interact with water because water, is polar and they're non-polar. And so the substances like this, they're not going to mix with water. So a perfect example would be oil. Okay, so oil and water do not mix, right? So if you get if you're making a salad dressing and you have oil and then you have vinegar or something like that that's water based, you'll notice that they form layers, right? So you have to really shake it up in order for them to kind of mix together, but then if you leave it for a while, they separate again. And that's because the oil is hydrophobic, okay? It's filled with these non-polar covalent bonds. And so because of this polarity, we can see, certain substances are able to dissolve within water and certain substances are going to be afraid or fear water. We also know that with water occurs in three forms. You can find water as a liquid form, okay, that you might drink water, as a gas form in the form of steam, and then as a solid form in the form of ice. And what's interesting about ice is that when we have these hydrogen bonds between nearby water molecules, as those hydrogen bonds break and reform, okay, they will start slowing down as the temperature slows down, okay? So imagine all of these little water molecules. These water molecules, if the temperature's at, room temperature, the water molecules are moving, okay? But as the temperature starts to drop, then the water molecules start to slow. And since they're slowing, we end up with the hydrogen bonds between the water molecules sticking or staying together longer. And when they do that, the hydrogen bonds form like a lattice structure with our water molecules. So you almost get like a little crystal here where you see here's one water molecule, here's another, and then they're connected with this hydrogen bond. And then here's another one over here and another one over here. So you end up with this kind of crystalline lattice structure. And because of this, since the hydrogen bonds are kind of putting everybody in place, they tend to be more spread out than if these water molecules are moving more because the temperature is warmer. So they're constantly breaking, reforming these hydrogen bonds. So the liquid state, the water molecules will be kind of closer together because they'll be constantly forming, reforming hydrogen bonds with nearby water molecules. But once those water molecules start to slow because the temperature slows, then you end up with that crystalline structure where they're kind of as far apart as possible. Okay. And this allows the unique ability of our solid form of water to be less dense than the liquid form of water. And that explains why ice floats, right? So if you have a cup of water and you put some ice cubes in there, the ice will be at the top, right? So it'll be floating. Okay, so that allows that ice to float on top. And I actually have this is from your textbook. The link for this is in the Openstax textbook. And you can just see how, when ice forms, you can see how far apart those hydrogen bonds are holding the water molecules apart. Okay, and so you end up with very, open area in between, and so it becomes less dense than liquid water. Okay. So that is what happens when the temperature drops. Well, what happens when the temperature increases? So if we have water molecules, they're constantly breaking and reforming hydrogen bonds with nearby water molecules in a liquid state. Eventually, if the temperature rises enough, the water molecules are going to start to separate, and you end up with evaporation. Okay, so evaporation occurs when more bonds between water molecules are broken than are formed. And so since these bonds are no longer present, that's going to allow the individual water molecule to be released. Okay, so that's when we get like steam from a boiling pot of water. Okay, so the steam coming up is just those individual water molecules. They are forming less hydrogen bonds to the point where they're kind of breaking free of each other. Okay. So all of this is unique to water. I mean, we don't see other substances like that. Like, for example, we'll talk about carbohydrates in the next video. So carbohydrates, they are, solid, and so it's, they're not going to have all these different properties of water where they're, liquid, solid, gas, that kind of thing. So water is a unique molecule in that form. Okay, so it floats in its dense, the solid form floats on top of the liquid form, and then we have the evaporation taking place with the gas form. Another property of water is that water is an excellent solvent. So that term solvent means that it's basically a substance capable of dissolving other polar molecules and ionic compounds. So we talked a couple of slides ago how polar substances that interact readily with or dissolves in water are hydrophilic. So this leads to this idea of water solvency. So a solvent is the substance that the solute is being dissolved in. So in this case, water is kind of the universal solvent because it can dissolve a lot of different solutes. And that solute, examples of solutes would be polar molecules and ionic compounds. Okay, and the reason for that is because of water's polarity. So we can see here, here we have our water molecule. So remember, with the water molecule, it's polar because it has a slightly negative end and slightly positive ends. And because of that, it's going to be able to surround, in this case, it's surrounding table salt. So table salt is NaCl. We have a sodium atom and we have a chlorine atom. And the sodium and the chlorine, they will come together to form an ionic bond. So that's something that we kind of talked about in the video 2.1, the last video. And we know that the ionic bonds, they're fairly weak because the sodium ion, in this case, Na+, is going to have, it's basically lost an electron so that it can drop down to its to a different shell, electron shell, that will be full, which would be its happier state. So we have this cation over here, and then chlorine would gladly take that electron that the sodium wants to get rid of. And once it gains that electron, now we have a chlorine ion. In this case, it's an anion because it's negatively charged. So once we put salt, NaCl, this weak bond, into water, the water molecules are going to start surrounding and breaking that ionic bond, okay? So you can see here we have chlorine, and chlorine being negative, it's an ion, it's an anion. And then we see the hydrogen ends of the water molecules. They're going to be really attracted to the chlorine because they have a partially positive end. And so you can see it's called like the zone of saturation, where we have basically water molecules surrounding an ion. Same thing over here with the sodium. We have our sodium ion, so it's positively charged. So the partially negative ends of our water molecules will be attracted to that. And so we have this other zone of, it's like a hydration zone or zone of hydration, where the water molecules are surrounding the cation. And in doing so, you can see that basically just this little atom is surrounded by water, and this atom is surrounded by water. So it has the solute, the salt, has dissolved into the water. It's surrounded by water. So water is an excellent solvent. So it particularly capable of not just the ionic compounds like our NaCl, but also other polar molecules. Okay. And then another unique property of water is that water is cohesive. So what that basically means is that because of the polarity of water molecules, they're going to be attracted to each other, right? So water molecules, the oxygen end of one water molecule will be attracted to the hydrogen end of a nearby one, forming hydrogen bonds. And because of this, we end up with water molecules. They are kind of sticking together. They're forming kind of an attraction. And we call this cohesion. So cohesion are intermolecular forces. So remember, inter, that would be between. Molecular, think molecules. So between molecule forces between water molecules caused by the polar nature of water. So it's just having these water molecules being attracted to each other. We have this kind of force that kind of sticks them together because of those hydrogen bonds, right? And what ends up happening though is that these water molecules, when they're kind of sticking together like that, they can form something called surface tension at the surface of the water. And so that's where the water molecules, they're pretty much stuck together because, you know, there's just air up here and then the rest is all these water molecules that they're going to be attracted to. So you end up with this surface tension at the surface of the water. And because the water molecules are kind of sticking together, we can actually place something that is very lightweight on top of the surface of the water, and it stays there, okay? And the reason why it stays there is because the water molecules are so, close together, they're not going to be wanting to escape each other. And so they're kind of blocking, prevents the item from being pushed through to sink to the bottom. Okay, so that's what surface tension is. So we can see, like here we have this little needle that we've placed right on top of the surface of the water. And you can see that the water molecules, they're right underneath. So they've kind of formed like this barrier almost to prevent that needle from sinking into the water. Something very similar to cohesion is adhesion. So in adhesion, you have water molecules being attracted to other molecules. So cohesion is water molecules being attracted to each other. Adhesion is water molecules attracted to other molecules. Okay, so a perfect example of this would be like if you have some sort of like small tube, or if you are, working in some sort of biology lab where you have a test tube or something like that, you'll notice when you're looking at the water level inside that test tube, you see how the water, it's not horizontal in the test tube, the surface of it, it actually edges up and clings to the side of that test tube. And because it's clinging to the side, that's this adhesive force that's taking place. So the water molecules are attracted to the side of the test tube, so they're sticking to it. Okay. So adhesion, think water molecules attracted to other molecules. Cohesion, water molecules attracted to each other. And then finally we get into pH, buffers, acids, and bases. So since water is the universal solvent, lots of things can dissolve in there. And so when we have a molecule that when it's in water, it will release hydrogen ions into the water, or whatever solution we're in, and increases the concentration of hydrogen ions, we call that molecule an acid. Okay, so acids, they add hydrogen ions. So hydrogen ion is H+, okay, so it's basically a hydrogen atom that's lost its electron. Okay, so this hydrogen ion is now in the solution. Okay, so if we have lots of hydrogen ions in the solution, we end up with an acidic solution. Okay, now on the opposite end, we can have a base. So a base is some sort of molecule that donates a hydroxide ion. So hydroxide, if you take a look down here, is OH negative. So this would be an anion, okay, so a negatively charged ion. So hydroxide ions, if they are released into the solution, we end up having the excess hydrogen ions that are in the solution attracted to them. And if they're attracted to them, then the excess hydrogen ions, they'll bond with the hydroxyl ions to form water. So bases, they're essentially removing hydrogen ions from the solution. And that makes it more of a basic solution. Okay, so you can see here how we have our hydrogen ions, we have our hydroxyl ions. So if we have an acid, we're adding hydrogen ions to the solution. Okay, so there's going to be a greater concentration of hydrogen ions. If we add a base, then we're adding a bunch of hydroxyl ions. And those hydroxyl ions, they will bind with the hydrogen ion to form water. So it's essentially removing that hydrogen ion from the solution. Okay, so acids versus bases. So what does this have to do with that pH scale that you probably learned about in elementary school? So our pH scale goes from 0 to 14. And what it's actually measuring is the concentration of hydrogen ions within the solution. So it's the lower the number, the higher the concentration of hydrogen ions. The higher the number, the lower amount of hydrogen ions in the solution. So if we're just looking at this from just looking at this figure over here, we have 0 to 14. Anything less than 7, so anything from 0 to less than 7, this area, these are what we consider acidic. Okay, so acidic basically means that they actually have more hydrogen ions in their solution than hydroxyl ions. Okay, so if it's less than 7 on the pH scale, it's going to be acidic, where we have a higher concentration of hydrogen ions to hydroxyl. Okay, so there's more hydrogen ions present in tomato juice, okay, than hydroxyl ions. There's more hydrogen ions present in lemon juice than hydroxyl ions. So these are considered acidic. Now on the opposite end of the scale, the higher the number is where we end up with the more basic solutions. And that will be the opposite of an acid. So anything greater than 7 has less hydrogen ion concentration to hydroxyl ion concentration. So there's more hydroxyl ions in ammonia than there are hydrogen ions. Okay, there's more hydroxyl ions in soapy water than hydrogen ions. So these are considered basic solutions. And then finally, right in the middle of our pH scale, pH 7, is neutral. And so things that are neutral have equal amounts of hydrogen ions to hydroxyl ions. Okay, so for example, our distilled water has an equal amount of hydrogen to hydroxyl. Okay. Now another thing that you'll want to note from this scale is, let me go back, is that it's a logarithmic scale. Okay, so that means that every time we move one place on this scale, we're increasing or decreasing the hydrogen ion concentration by a factor of 10. Okay, so for example, if we're talking about urine, ooh, that's lovely. Urine has 10 times more hydrogen ions concentration than distilled water. Okay, black coffee has 10 times more hydrogen ions than, say, urine. Okay, so as we go down the scale, you can see these are going to be very strong acids because they have a really high concentration of hydrogen ions. Now, if we're comparing, say, gastric acid to orange juice, okay, we're moving twice on our scale, right? So each time we move, it's a factor of 10. So if we're comparing gastric acid and orange juice to each other, gastric acid has 10 times 10 or 100 times more hydrogen ions than orange juice. Okay, so you can see how every time you move up the scale, you're moving up by a factor of 10. Okay, so 10 times more, gastric acid has 10 times more hydrogen ions than lemon juice, but 100 times more hydrogen ions than orange juice, and 1,000 times more than tomato juice, and 10,000 times more than black coffee. Okay, so every time you're moving up, multiply it by 10. So 10 times 10 times 10 times 10 equals 10,000. So that's why gastric acid has 10,000 more hydrogen ions than black coffee. Okay, so it's an inversely proportional logarithmic scale. And then finally, the last part of this chapter gets into buffers. So buffers are basically substances that they either will accept hydrogen ions or they will donate hydrogen ions, typically. Sometimes they'll donate hydroxyl ions. So by doing that, they're removing the hydrogen ions from the solution when there's too many. Okay, so if you add more hydrogen ions into the solution, you're adding an acid to the solution, the buffer will absorb those. And so even though you're adding acid, the pH is staying the same because the buffer is absorbing the excess hydrogen that gets added. So buffers, it's a substance that resists the change in the pH by absorbing or releasing hydrogen or hydroxyl ions. Okay, so within nature, buffers are very, very important in helping maintain homeostasis. In this case, homeostasis being maintaining the pH level. So in our bodies, our blood pH ranges from about 7.35 to 7.45, which makes it slightly on the basic side. Okay, so it's right about there. So it's above 7, so it's slightly basic. Okay. We want to keep it there. We don't want to suddenly have a bunch of, we don't want our pH levels to drop too low, because then you get something called acidosis, and that can make you sick because our enzymes and everything kind of functions in around the same pH. So if the pH is rising too much or lowering too much, that can put you in harm because you're not able to maintain homeostasis, okay? And that affects enzymes and how things work within your body. And so we have to resist that change. We have to prevent the change from happening. So we have this buffering system within our blood that helps keep the pH of our blood stable, even if we're adding an acid or a base to it, okay? So here's an example. Over here, you'll notice we have 2 ions. We know they're ions because there's a positive charge and a negative charge. So we already know what this ion is, okay? So this is a hydrogen ion. So hydrogen ion H+. Over here, this is called bicarbonate. Okay, so bicarbonate is a negatively charged ion. So we have bicarbonate. Now, when these two are in solution together, they will form carbonic acid. Okay, so carbonic acid is just a molecule that could be present within our blood. And then this carbonic acid can further break apart into water and carbon dioxide. So let's say that we have an excess amount of hydrogen ions in the solution. Okay, so inside our blood, we end up with too much hydrogen ions. Well, these excess hydrogen ions will bond with the bicarbonate. And so by bonding with the bicarbonate, they're going to be forming carbonic acid. So it's removing the hydrogen ions from the solution. Okay. So if we want to just get rid of all of that, then that carbonic acid can then further break down into water and carbon dioxide, which we can release the carbon dioxide in the atmosphere when we exhale. Okay, so this is allowing us to get rid of that excess hydrogen ions. And so our pH level will pretty much, it will remain in that 7.35 to 7.45 because of this kind of buffering system that we have. Okay, when we have too much hydrogen ions, it ends up bonding with the bicarbonate. And then that will form this molecule that gets broken down into carbon dioxide that gets exhaled. Okay, let's say that we had the opposite occur. For example, let's say like if you've ever hyperventilated, you've basically, a lot of times, like if you have a panic attack or something like that, you're breathing out so fast, so much carbon dioxide. So if you've breathed out too much carbon dioxide, then you have removed a lot of basically the acid part of, or you're releasing too much hydrogen ions into the solution. So that will cause our carbonic acid to break apart to form or to release more hydrogen ions into the pH. So that'll prevent your blood from the pH from becoming alkaline or a higher pH. Okay, so it kind of works both ways. So if our blood pH becomes too acidic, we can get rid of that excess through the buffering system to bring it back to the normal zone. If we end up having too much, or we've lost too much carbon dioxide and we end up with too alkaline blood, then we have that carbonic acid that can release hydrogen into the solution. Okay, so that's a unique way to keep our blood pH right around 7.35 to 7.45, even if things are changing around us. Okay, so we have a few review questions to end here. So which of the following statements is not true? Is it 1, water is polar? 2, water stabilizes temperature? 3, water is essential for life? Or water is the most abundant molecule in the Earth's atmosphere? So which one of these is not true? if you thought this last one was not true, I would agree with you. Okay, so water is actually not the most abundant molecule in Earth's atmosphere. It would be nitrogen. Okay, actually, I think our atmosphere is like 78% nitrogen. And it makes sense because when we breathe, we're not basically inhaling a bunch of water, right? If it's the most abundant molecule, then why would we be needing to drink at all? We just breathe and get all this water. So no, water is not the most abundant molecule in our atmosphere. So that's the incorrect one. We do know that water is polar, okay? Holding the oxygen and the hydrogen atoms together is a polar covalent bond. We know that they stabilize temperature. So basically the hydrogen bonds that are forming in between the molecules, they're forming, reforming, so it's going to make the temperature is not going to fluctuate as quickly because of those hydrogen bonds. And we know that water is essential for life. Every living thing requires water. So it's this last one that's not true. Using a pH meter, you find the pH of an unknown solution to be 8.0. So how would you describe this solution? If it's 8.0, does that mean it's a weak acid, a strong acid, a weak base, or a strong base? Okay, so what type of solution would you categorize as? Weakly acidic, weakly basic, or strongly basic? So if you chose weakly basic, I would agree with you. So remember with our pH scale, we go from 0 to 14. The higher the number, the more basic. The lower the number, the more acid. So anything above a 7 is going to be basic. In this case, 8 is just above 7, so it's considered weakly basic. Okay. And then the last question, the pH of lemon juice is 2.0. Whereas tomato juice pH is about 4.0. So approximately how much of an increase in hydrogen ion concentration is there between tomato juice and lemon juice? Is it 2 times, 10 times, 100 times, or 1,000 times? If you chose 100 times, I would agree with you. So remember, our pH scale is a logarithmic scale. So every time we move up the scale by a factor of 1, we're actually increasing or decreasing, in this case decreasing the hydrogen ions by a factor of 10. Okay, so when we're comparing tomato juice and lemon juice, tomato juice orange juice has 10 times more hydrogen ions than tomato juice. Lemon juice has 10 times more hydrogen ions than orange juice. So if I'm comparing these two to each other, tomato juice and lemon juice, we have to go 10 times 10, or 100. Okay, so lemon juice has 100 times more hydrogen ion concentration than tomato juice. Okay, so 100 times more. All right, so that's it for chapter 2.2, so the middle part of chapter 2. So by now, you should be able to describe the properties of water that are critical to maintaining life. So think about water's polarity, allowing, hydrophilic substances. We have water being the universal solvent. We have water being less dense in its solid form, and so forth. So all of these are unique properties that allow us to survive. So it helps maintain life. Okay. The next video I have is going to finish off chapter 2 with biological molecules. So please, continue watching. Easiest way to locate this video is if you just click the subscribe button. That way you can just easily find it in my playlist.